Well, I'm John Halloran, and my job is to introduce our next speaker, Alan Taub. Alan is professor of material science and engineering and mechanical engineering, and he's a highly distinguished member of our community. Amongst many honors, he's a member of the National Academy of Engineering, and you're on like a board? Council. So he's even running that organization. But he began as a material scientist at Brown, got a bachelor's degree in MSc, went on to Harvard and studied applied physics, but working with Franz Papen, he was really doing material science. Metallic glass, which was rather new in those days. And after that, he went on to industry where he excelled. He went to General Electric in corporate research in Schenectady in those days. And among other things, he worked on superconductors, niobium-10, to make actual niobium-10 magnets, and contributed to magnetic resonance imaging magnets. Then on to the Ford Scientific Lab, which he began by managing material science for Ford, but then took on more responsibilities: crash safety, engineering of the Lincoln vehicles, and finally went on to General Motors, another company that starts with, you need to get General Mills in somewhere in your career. General Motors Science Lab went up the ladder until he was at the very top as a vice president of global research and development. And in General Motors context, global means truly global and a very large endeavor. From the point of view of us academics, I'm glad to say that in 2012, Alan finally got a real job and became a university professor here at Michigan. In addition to doing the normal things that university professors do in our little laboratories with our graduate students, carbon fiber, reinforced with carbon nanotubes, stuff like that, he could not stop from working on a larger scale and led a rather large proposal effort that resulted in LIFT, Lightweight Innovations for Tomorrow, an organization he serves as Chief Technology Officer. It's a public-private partnership that's looking not just in research and development, but throughout the entire supply chain and labor force. It's a rather large program that I think he'll tell us about now. So thank you very much, Alan.
Thank you, John. I do have to blame Jack for the LIFT initiative. It was my first week after joining U of M, and Jack had the wonderful idea, why don't you lead a proposal team? That's right, it was even before I joined. Rachel, I don't know how to unblank the screen. So it's really a pleasure to be here. Thanks for the introduction, John. It wasn't quite Max's yesterday for Steve, but he truly is a god. What I want to talk about today, and I think it's along the lines of what went on yesterday, is more around structural materials, and in particular, how weight reduction plays in improving transportation efficiency. And so, you know, as John mentioned, I started my career in GE, among other things, worked on turbines, both land-based and for aircraft engine. And when I moved to the automotive industry, one of my biggest surprises was the inefficiency of vehicles. 68% of the energy in the gas tank is lost during the combustion process. And by time you look at the rest of what occurs in the powertrain, for every 100 joules of energy in the gasoline, only 17 joules actually gets to the wheels to move the vehicle. And of that, about a third of it is pushing air out of the way. A third of that is heating up the tires and the pavement. And only 1/3 gets turned into kinetic energy. So the key is lots of work going on here. By the way, this is the reason why the end game for vehicles is electrification. It's a much more efficient transition of chemical and other energy into motion. The key is getting that more cost-effective. On the other hand, independent of what the powertrain is, lowering the weight makes the vehicle move more efficiently, or in the case of commercial vehicles, I get to do more payload, or in the case of military vehicles, I get to do more mission. So reducing weight is critical. A good rule of thumb, 10% weight reduction of a vehicle will give you 6% fuel economy. So if you are the chief engineer on a program, which I actually had the luxury of being at one point, you get a target to deliver the fuel economy of your vehicle. Your job is to do that at the highest value to the customer, meaning achieve that fuel economy at the lowest possible cost. And what you're doing is trading off the losses that I talked about before, better aero, better propulsion, and within that competition, you look at, and this is something I often ask my students to do, is go calculate what the value of a pound reduction or a kilogram reduction on the vehicle is worth. To the consumer, it turns out coincidentally, it's about the same number of about $2 per pound saved. That makes it competitive with the other actions. So just remember that $2 per pound saved is the target. Interesting, I got involved in this in that institute John mentioned. We're working on reducing the weight of all the machines that move people and goods, not just on land, but land, sea, and air. So I'm learning a lot about ships, working with our naval architecture folks, and airplanes. If it's worth $2 to take a pound out of a vehicle, it's worth $200 to take a pound out of a commercial aircraft. By the way, it's worth $20,000 to take a pound out of a satellite. That is what it's worth to reduce the energy for it to accomplish its mission. So there's two ways to do that. The first was taken on by the mechanical engineers of the world. Remember, I do have a dual appointment. My minor was in solid mechanics, but I do believe mechanical engineers look at the world differently than materials engineers and scientists. They'll build an FEA model, and I'll show some of those later, and the materials are continuum. We as material scientists look at the microstructure underneath, but in a world where in most OEMs, and I've been in 3 of them, they're dominated by mechanical and electrical engineers. Material substitution is their solution of last resort because of all the risk it has getting the supply chain going. So the first thing you do is better design. And what really happened in the automotive industry that helped to make that happen was topology optimization, just removing material where it wasn't required. Almost all of that low-hanging fruit has been accomplished. So what is the industry doing now to get that next step? It's using materials with higher specific strength and higher specific modulus. It's now at the point where it has no choice but to go in that direction. There have been prototype vehicles in labs for 30 years or longer, which have shown the kind of weight reduction you can get against what was the baseline material for vehicles, which is low carbon steel. We've known that for decades. We've also known that each of those material substitutions comes at a cost. The problem is the incremental cost for most of these substitutions is above that $2 per pound saved, with one exception, and it's the introduction of higher strength steels. And in particular now, it's interesting that steel industry went through what they called the Generation 1 advanced high strength steel. They tried Generation 2 and it failed. Now jumping to Generation 3, it is the one material that lets you do that substitution at acceptable cost, and I'll go into that in detail. Metallurgy these days doesn't make the cover of Science very often. We try. I don't know if you had a Science or Nature cover, you know. But we do make the Wall Street Journal often, and it was just yesterday. Automakers find strength in steel, and the battle for aluminum and steel is back on. By the way, we got more columns than the battery article. Right? So it's been a long-term battle, but the key is the materials and the alloying elements in these structural materials, they are not rare. We are not talking about fundamentally hard-to-find materials. The reason they cost so much is because of their manufacturing process, either the energy to do extraction and refining or the cost to form them into the component structures you want. And so Jack mentioned, the government of the United States decided to create organizations, which they don't like to call it this, but I call it the analog of what the Fraunhofers have done for industry in Germany. A public-private partnership where you connect universities and companies and national labs to perform research on manufacturing. And in this case, reducing the cost of lightweight metal substitution. We were granted $148 million to found the organization. $70 million came from the federal government. We raised $78 million from companies in the state of Michigan. And I still remember this meeting. Dave and Jack sat me down and said, would you be willing to do this? I said, let me think about it. Came back and said, yeah, I'd like to pull together a team to go after lightweight materials. At the time, we included composites. But the first thing I'm going to do, and I remember John saying, go see Glenn Dane down at Ohio State. Yes, the Ohio State University we partnered with. By the way, the week of the game, we have no meetings at Lyft. But it really has been a strong partnership together with EWI. Our headquarters is actually located in downtown Detroit. We went into an area that was just about to gentrify. There were burned out buildings across the street. I was all ready to put security 24 hours. It's really nice to go down there. It's near the old Tiger Stadium. And that whole area is gentrified. In fact, we took an option for 15 years on our lease, which I'm sure our landlord is regretting to this day because we couldn't rent it today. We couldn't afford to be there. One reason I'm doing that is we have installed and recently put online pilot-scale metals manufacturing equipment, and that equipment is available for our students to use. And in fact, as long as a year ago, Professor Bonos and my students have been at Lyft doing experimental work. So if you need access to pilot-scale manufacturing equipment, please see me. I mean, we made that investment there, plus the university gave us $3 million to put new advanced equipment in the Wu Manufacturing Center down the hall. If you're not aware of these capabilities, please see me. But let's get back to the technology. We want to reduce the cost of introducing these advanced materials. So if you look at automotive, it has gone through a major change in the last 20 years that exceeds the material change that occurred in the prior 80. Anybody want to guess what the first primary material in the first vehicles that were produced for the structure of the vehicle? Wood. There was actually a battle between aluminum and steel in those early days. And by the way, Detroit in southeast Michigan was the Silicon Valley of the early 20th century. There were startup companies, I think there were close to 100, and they eventually grew up to be the GMs and Fords, just like you have the Googles and Apples today. But that low carbon steel, easy to manufacture. At the time, gas was 10 cents a gallon. Nobody worried about the cost and efficiency. And easy to join. The challenges that Jack would have had with low-carbon steel were solved in 10 years. What's happened is the majority of the material substitution that has occurred has been the substitution of high-strength steels for low-carbon steels. As you know, when you alloy, you don't change the modulus that much, but you change the strength. If you make something stronger, you can make the sheet thinner, and you make it lighter. And the key is those substitutions can occur for less than $1 per pound saved. Remember that $2 per pound target? So that has dominated the material change in the industry. I lived through General Motors historically being the heaviest vehicles in their segment, to a focus to become the lightest vehicles in the segment. The Cadillac ATS was the first time we paid attention to that seriously and accomplished it, became lighter weight than the Mercedes and the BMW. Most of that was driven by the high-strength steel, but you can see the inroad of aluminum. And the reality is U of M got out of research and materials for steel quite some time ago, but we are very active with our colleagues in aluminum, magnesium, and titanium, so I'm going to concentrate on that. I mentioned in the beginning of the industry, there was literally a battle between what was going to replace wood. Steel won. And what's interesting, you're in the early 1900s. Aluminum is expensive because it takes so much energy to make it. It's hard to form, and it's hard to join. Found this 50 years later, same problems. We're in the beginning of the 21st century. We've learned how to form it. We've learned how to reduce the cost of making it, and learned how to join it, first using mechanical fastening, and then the industry, through some efforts of Jack's group, we've actually learned how to use conventional spot welding to join it instead of having to change over the entire joining infrastructure. So one of the biggest bets in material substitution in our industry is the Ford F-150. It is the largest selling vehicle in North America. And if you look at it in volume, one of the largest selling vehicles in the world. It is a vehicle that is abused. It is a work vehicle. And it was a very, very bold move for Ford to make this change. By the way, the part you don't see underneath is the frame that holds this vehicle up. That's all advanced high-strength steel. Those of us in the know, this vehicle was delayed in its production release, which, by the way, can cost a company $2 to $3 million a day for every day it's delayed. Everybody assumed it was the aluminum. They put, by the way, John, I believe this is true. I was a GM at the time. They had put their best metallurgist on the aluminum body, and it was the advanced high-strength steel frame that they had messed up, which delayed production. But the key is we can do this today. It still costs more. It's at that borderline of, depending who you ask, $225 to $250 a pound, but we're ready to do it. And we're ready to do it on high-volume vehicles. And so what I want to do is take a small diversion now and talk about one of the two revolutions that's occurring in structural materials research. One of those revolutions, John Allison will talk about later, which is ICME, the ability to locally control properties. The other one is agile, low-cost manufacturing. So a little bit of philosophy. The Industrial Revolution comes along, and blacksmiths, which have been forming parts in metals for hundreds of years, were replaced by million-dollar machines that could apply very high forces over large areas all at once. The reality is, a good blacksmith could make almost any part we make today by that very expensive process. Again, million-dollar machines and tools and dies for $100,000 each. It is the right way to make things if you want to produce 100,000, 1 million a year. But the world is becoming personalized. We as manufacturing people have become hooked and addicted to this approach. And one thing we're looking at is Glenn Dana's used the term metamorphic manufacturing. If the first manufacturing was subtraction, meaning machining, additive manufacturing, and we'll hear about that from Jody, this is the idea of metamorphic, changing the shapes of metals and materials using local deformation. So what does that mean? What's the difference between, say, what a stamping machine does and a blacksmith? A blacksmith can control temperature locally and will do the deformation locally. That allows you to get around the need for very strong dies because you're not using high forces and very expensive machines. Here is a process we've decided to take the lead on at University of Michigan. It's called incremental forming, and in particular, incremental sheet metal forming. So instead of having this die and pushing all the metal down at once, you can take a traditional CNC milling machine, take basically a 1/4-inch steel tool that's rounded at the bottom, and spiral it into the sheet to form your part. No tool required, standard equipment. And the question is, how fast can we run this? What kind of tool path do you need to have to make the part form in the shape you want? And what are the properties of the final part? So where do we see this playing? At low volumes, it is even though it's slow, by the way, faster than additive, and you can get the same kind of properties from hot and cold work material. So we cannot have to worry about additive, which basically produces cast properties. We can get cast and wrought. It's the same starting material deformed in a similar way, and it has those advantages. At the university, we've set up 3 ways to do this. I took on the easy part, which was symmetric parts in a lathe. Junice set up to do it on a milling machine. And one of the things I find that's intriguing now being a professor is, June and I got together, we decided we're going into this, and one of our graduate students discovers that actually Wes McGee over architecture got into it years before. What do you mean? Went over to see Wes, who's now part of our team, on an MQ project, making building facades. Right? Now you're in tailored, you want to make 2 of these. A perfect way to do it, and he went much more elegant with dual robots, a master and a slave doing this. So we have the full complement of capabilities in this, and clearly we need to understand how to model and predict deformation and behavior, so we teamed up with Professor Banu over in ME, and going after the typical way you go after metal forming, using FEA analysis to say, can we predict the shape that's formed? The real goal, can we predict the spring back, the final shape you get, not just the tool path? We quickly set this up. There were others we teamed up with. By the way, we have a project going on with both Northwestern and Ohio State doing the modeling. The key is using very simple FEA tools. We were able to predict the shape and, more importantly, the thickness of the finished part. As you deform it, you stretch it, the thickness gets here. Here's a 45-degree cone, and you can see the model very nicely predicts the thickness and shape of the part. What's even more impressive, given the simplicity of the constitutive law we put into this model, near the formability limit, you actually get a thinned region when you start doing the forming, and it predicts that thinning quite accurately. That was something we knew we could make work, and in fact, we made it work pretty quickly. The key is, though, and you'll see this when John gives his talk, I assume, we have to, and I'm an experimentalist, in order to do the modeling, we had to use our metallography techniques, including some very elegant EBSD that, in fact, Maya Nassen was doing, in order to say this is the starting grain structure, this is the starting texture. And by the way, as the process evolves, not modeling the texture evolution, but we had to do and provide the input of how the texture changes so that the FEA could put in the right numbers. Our goal is to be able to predict the texture evolution and using some of the newer ICME tools. Fortunately, what Maya found was, at least in the specimens we've been looking at, the grain structure changes proportional to the sheet elongation. So we didn't really find any surprises there. We do think at some higher deformation, we're getting some recovery and recrystallization, but basically the grain size is mirroring the stretching of the sheet. But here is, and I said I'd make some interesting remarks about how a material scientist approaches a problem like this rather than a mechanical engineer. Maya was showing some fracture surfaces. We were looking at the structure. I said, wait a second, in the SEM, what's that on the side? It turns out nobody, and this field's been active for a decade, was looking at the surface finish of the parts. And what she discovered was, not surprisingly, and this is something we're looking at hard, you have instead of having a stamping die or a deep drawing where the die is basically pulling the material, we're basically doing a wear test. I'm taking a pin on disc and spiraling it through the material. So lots of tribological features on the tool side. And we have a concern of what that means for fatigue. The project we're doing is with Boeing and Lockheed Martin, who are worried about that. But then more importantly, looking at the other side, we're actually seeing some surface cracks. And so what we know is the strain path is different in stamping than in incremental forming. That leads to different microstructure evolution. That leads to different properties and different surface finish. And we really need to look at fatigue critical parts, so that's what we're going after next. Changing other topic is, what about castings? This is what I've talked about is sheet. What happens if we're trying to make lighter weight castings? Cast iron, just like low carbon steel, was the baseline for castings on vehicles. Basically on the engine side, pretty much replaced by aluminum. Some indications we may even go lighter with magnesium, similar on chassis parts. So how, are we done? No. If we can make, in our case, the aluminum alloy stronger or higher modulus, we can decrease the wall thickness and make the casting lighter. People had been doing that by putting in 10, 20 micron particles to refine grain size, and so to have a dispersoid strengthened casting. The key is, even though I'll argue metallurgy has been dealing with nanomaterials forever, we just didn't call it that because that's what nature provides. We found if you put in, working with our colleagues at Worcester Poly over in Massachusetts, if you can put in nanometer scale particles, and John, we actually call these ceramic particles, even though they're not oxides, you can get dramatic improvements in strength. And more importantly, we can retain the properties to higher temperatures. And that's really the goal. There are lots of intermediate temperature applications where we would like to replace the castings with aluminum or go to thinner wall, and this can enable it. The problem is, and it's actually the inverse problem of what Sharon Glotzer talked about yesterday. Our problem is not how do the particles collect. Our problem is dispersing them because they don't want to separate. And so the traditional way of doing that, by inserting the particles in the melt and ultrasonically disperse them, really is not proved to be very effective when we get down to 50 nanometer particles. And so, and we don't take credit for this, it came from Worcester Poly, Durana Paley in there. Wait a second, can't we form the particles in situ in the melt? So they start off naturally dispersed. They came up with the idea of bubbling nitrogen through the molten aluminum. It reacts in situ and forms aluminum nitride particles. They then showed, oh, what happens if and they are of the size we want. They can bubble methane, or actually CO2, into an aluminum alloyed with a little titanium and form titanium carbide. So we now have a way that worked at lab scale to produce nanoparticle reinforced aluminum. We have the role of characterizing both the microstructure and the properties there. You can see we do form aluminum nitride particles. The thing is now we're trying to scale it up. And one of the things that Jun Liu and Caleb Reese, who are postdoc and graduate student on this, found very recently is the same operating conditions. At least we believe they're the same operating conditions. And we get nicely spherical particles in one case, and all of a sudden we're getting acicular plates for basically the same conditions. And so we started an activity here, working with Professor Shahani and Rachel Goldman. We better understand the reaction that's occurring between the nitrogen bubble and the melt. And we're just getting this going, looking at some different techniques. How do those particles nucleate? How do they break up? What is controlling the morphology of the particles? So stay tuned for that. Going to switch to another material we're investigating, carbon fiber composites. It is the way to make the lightest structures. It is also the way to make the most expensive structures. Remember, $2 a pound for automotive, $200 per pound saved for aerospace. It's no wonder that therefore the baseline material for aircraft became aluminum right away. It almost went straight from aluminum, from wood to aluminum. They're now trying to make the transition to carbon fiber. And I will tell you, when I was at GM, we had a joint venture laboratory. We owned 50-50 with Boeing, so I used to interact with John Tracy, the CTO there all the time. And that plane is costing them a lot more to make than they thought it would. So the key is, how can we reduce the cost of the carbon fiber? Lots of people going after reduce the cost of the fiber. Other folks going after how do we improve the molding time? Both of those drive cost. What we're going after is how do I improve the mechanical properties of the composite by strengthening the polymer matrix. And so it's been known, one of the earliest ideas about using carbon nanotubes was strengthening polymers. And so the key is, could we add that to the matrix of a carbon fiber composite, and by increasing the strength of the matrix, increase the load transfer and reduce the amount of carbon fiber to get the same thing? That turns out, at least on paper, to be economically attractive. And what we wanted to do was actually not only add the nanotubes, but align them in the direction in which the stress was applied. Several ways to do that, and I'm now suffering with what I now realize professors have to deal with. I spent most of my career on the receiving end of graduates, and that was great. I now have my first student leaving. Just when they get good, they leave us, right? But Wes looked at, we came up with a way, collaborating with Professor Lahan and Kiefer on their Raman spectroscopy, to do real-time measurement. This was the first time it was done of carbon nanotube rotation under different applied fields, whether it was electric, magnetic, or shear. We found we could fit it to nice exponential functions. And because I tend to look at kinetics, was hoping, oh geez, these are nano in one dimension. Maybe we don't look like it's macroscopic or microscopic rotation kinetics. Turns out the rotation, even because we're long in one direction, is actually controlled by the same kinetics, which is the viscosity of the medium it's in. But then he found something else, which for months I kept saying, this is experimental artifact. There's something that's not making sense here. He was doing electric field alignment, and as the electric field gradient went up, not only was it going faster, but it was reaching different plateaus. And in fact, it was reversible. It was acting like a state function. I said, wait a second, you know, I understand mechanics, I understand diffusion. You put a different gradient on it, it should just happen faster. It shouldn't get to a different end state. Wesley stuck to his guns and actually was able to prove that this was due to the length distribution of the carbon nanotubes, because the driving force and the torque depends on length, and in this case, so does the polarizability. This is due to different populations based on length of the tubes aligning. So the good news is we now understand the kinetics, we understand what it takes to drive them to align. So what happens if we want to induce that alignment inside a carbon fiber composite? We're just at the point where this is starting to work. Interesting thing, which in retrospect should have realized from the beginning, carbon fibers are electrically conducting. By definition, electrical conductors can't sustain a voltage gradient. What that means is along the length of the tube, near it, I don't have a voltage gradient. What that also means is, as a COMSOL model, I get a harder gradient right at the edges. Well, that's where you want to, in fact, have the increased load transfer. So it turns out nature is in the right direction. And in fact, the Raman spectroscopy is showing the alignments occurring in the direction we want, in the location we want. The issue now is, in order to do the Raman, we're doing it at very dilute levels of the CNTs, so now he's going to be increasing it in the 2 weeks you have before you start your job and get this done. The other thing is, can we get the alignment for load transfer in between the carbon fiber toes? So just to finish up, you go, wait a second, am I just hedging my bet? I'm working on, and so are other people here, 3 different classes of materials. Is it just because I'm not sure which one's going to win? No. You go back as recently as 15, 20 years ago, the assumption was we were leaving low-carbon steel vehicles to other mono-material intensive vehicles. We now realize we've gotten much more sophisticated. No, the answer is the right material, in the right form, in the right thing. So all structures are becoming complex mixtures of materials, and we need to master manufacturing them in all these shapes with all the different materials. So with that, like everybody else, I've learned I don't really do any of the work, so thanks to my graduate students, and thanks for listening.